are somehow all a subset of what I would say is applied statistical mechanics. So we do quite a lot of work on coarse graining. We use Monte Carlo molecular dynamics in very different flavor. Some cases we also develop specific algorithm in terms of Monte Carlo algorithm for sampling. And then use of advanced sampling techniques is also something that it's used quite a lot within my group. So just to give you an idea of a few of the projects that we are running. So with Debesh Mandal, who's here on the call as well, we're working mostly on nanogels or on simulating nanogels for drug delivery. And more particularly, we're trying to look at how the structure of the nanogel determines the degradation rate. Fiona is working on DNA-based liquid crystal elastomers as for biosensors. Then with Daniele Visco, we're looking at everything related to multivalent nanoparticles. And in particular, we're looking at how can we tune, how can we design multivalent nanoparticle in order to have specific selectivity properties in terms of binding to be used, for example, in biosensing or drug delivery. And then I have 3 projects that I'm doing in collaboration with other professors and lecturers here at Imperial. So first is we're looking at, for example, the self-assembly of clays with Professor Sullivan in the civil engineering department. This is probably the project in my group that is farther from, let's say, from materials, but in a certain way, it's still connected to it. I'm working on basically the design of plasmonic nanostructure with Dr. Fang Shi, and in particular, William Morton. With him, we're taking care of basically the computational part. So how do we get the wanted plasmonic response? How can we design it given a specific target structure? And then with Professor Daniel Dini, who's going to be the speaker after me, where we have a project on polymer brushes and how can we control, let's say, the tribological properties of polymer brushes by changing the architecture of the brush itself. And then finally, the project I'm going to talk about today, it's actually something that we started in my group 2 or 3 years ago now. And it's basically on the use of polymer, well, on the development of polymer-based bioglues. And that's also basically the starting point for the talk today. So in terms of inspiration, I think everything started because of this paper that was published in 2014 in the group of Leibler in Paris. So what they've shown is that nanoparticles in general can be used as glues for biogels. And this is something that from a technological point of view, it's very difficult to accomplish. So in general, biogels are quite, let's say, quite repelling, and it's very difficult, especially to glue two different biogels together. Mostly because of the type of interaction that biogels, which are nothing, well, which at the end are hydrogels, so are water swollen gels, have between each other. Nevertheless, it was shown that nanoparticles, in particular silica nanoparticles, can be used in order to bind biogels together. And this is a clear application, for example, for the development of sutureless wound healing, as you can see in the pictures here. They're a bit graphical, but basically what you see in the bottom right corner, it's a comparison between a suture on a mouse skin done either using nanoparticles as a glue or using a normal typical suture, or Dermabond, which is a competitive polymer-based glue. Okay, so now one of the peculiar things about this is that colloids, I mean, the idea of using nanoparticle, or more generally colloids as adhesive, is not old, well, is not new, sorry, at all. And it comes from quite a long time ago, but it's pretty peculiar. Things are pretty peculiar because colloids has been used both as adhesive and also to prevent adhesion. So what we really wanted to try to understand is how does it work? Because it's definitely not only chemistry that matters. So it's not just the chemistry. I mean, the physicochemical interaction in terms of what is exactly the compound that we're using, but the same compound can be used both to either increase or prevent adhesion. And this is, for example, a very good picture in this sense, because in this experiment, what they are showing is the fact that if you look at the adhesion strength of the interface as a function of the concentration of nanoparticle at the interface, you have a non-monotonic behavior using nanoparticles that are basically of the same chemistry but different sizes. So this is what this C50, 75, A75, A30 are. So our starting point is, okay, I mean, we are doing soft matter theory, and we are going to use highly coarse-grained model to study this system. So there is nothing about the chemistry that we can really capture too well, if not trends. But we can use we can use coarse-grained model to try and understand what is, if there is any, the effect of other other controllable parameter, like the size and concentration or the shape of the nanoparticle. So 2017, so this was 3 years ago, we started to work on this with Dr. Nicola Molinari, who's now at Harvard. And we started with the simplest possible model that we could think about. So like we described our polymer network using effectively the Kremer gas model, which is a highly used model in polymer physics to specifically to describe the response of polymer network to elastic deformations. So it's nothing but affinity potential plus Lennard-Jones potential between non-bonded bits of the polymer network. The nanoparticle, we describe them using the purely repulsive interaction. This is to respect the fact that in solution, these nanoparticles would be completely stable, so they wouldn't coagulate, so there is no attraction between them, and we can just do it by using a cutoff and shifted Lennard-Jones. And then we have an interaction between the polymer and the nanoparticle that it's also described via simple Lennard-Jones potential. The idea here is to use the potentials as simple potential as possible so that we can understand a little bit more about, let's say, the soft metaphysics behind the problem. So we're not really trying to describe the chemical interaction in any possible way. And how do we do it? Basically, we prepare a system where we have a gel and we cut the gel into half and we put some nanoparticles in the middle. And then we do non-equilibrium molecular dynamics simulation where what we do is we strain the gel in the vertical direction and we measure the stress. And then we can get all the information we want from stress strain curve. Okay, so in this regard, when we were studying hard nanoparticle, so of the kind that were used in the experiment I presented before, we can distinguish basically the presence of two different regimes. So at low concentration, what we see is that effectively there is a minimum attraction between the nanoparticle and the gel required in order for the nanoparticle to act actually as a reinforcement, so to act as a glue. And below this minimum attraction, the nanoparticles don't act as glue anymore, but actually they prevent adhesion. Now, we were able to show in this paper that this depends on the fact that when we put nanoparticles on the interface in a gel, there are always two competing interactions. So the nanoparticle cause an elastic deformation of the gel, which actually prevents adhesion, but then they also have the binding interaction that is due to the fact that the surface of the nanoparticle will bind, is attractive to the gel. And the competition between these two determines the fact that there will be a minimum value for the attraction before any reinforcement is observed. Now, if this is we were able to come up basically with an equation that described the boundaries between reinforcement and weakening, but clearly this equation only at in the low concentration regime, because when you go to high concentrations, you see that the reinforcement is not monotonic anymore in the total concentration. So what I mean is at certain point, once you start to load the interface with nanoparticle, at a certain point, the system, instead of acting as a glue, suddenly drops its adhesion property and start to become a repellent again. And again, the beautiful thing about doing, let's say, simulation, as we all know, is that we can have a very good look at exactly what is the microscopic we have a picture of the system that can tell us something about the microscopic behavior or the microscopic origins of the macroscopic behavior that we can observe. And what we've seen is that in in our case, when you go from low to high to high density regime, you complete, first of all, you have a structuring of the nanoparticle at the interface. So when where you're in the low coordination regime, so this is like the top left figure, the nanoparticles are literally concentrated between the two gels. But when you start to go to higher and higher concentration, you have a layering effect, which is what you observe in the bottom figure. And this layering effect completely changes the typical coordination environment. So the coordination environment can be, we measure the coordination environment by looking at basically effectively how many bonds with the gel of one of the two gel you have with respect to the other, with respect to the two half. And it is pretty clear using this bridging parameter that when you go from very low to very high, to very high concentration of nanoparticle, things qualitatively change, and this can explain the response that we observe. Now, very quickly, so because the drop in adhesion at high concentration was due effectively to excluded volume interaction between the nanoparticles that determine the layering, one possible solution to that, so that we can push a little bit more the system, would have been to use soft nanoparticle. And when we talk about soft nanoparticle in soft matter, we typically talk about polymers. That's actually the name that we can give. That sometimes we give to polymer. They're called soft nanoparticle because effectively different polymers, depending on the architecture, act as nanoparticles that are soft because you don't have a potential that becomes infinitely repulsive at contact. And in general, we had two hypotheses. So first is that the soft repulsion would allow us to have higher packing, and then it should improve adhesion compared to use of hard nanoparticle. But obviously the second hypothesis that we also had is that adhesion should be dependent on the polymer architecture that we use. And so this is the reason why we started to study all sorts of polymer architecture that can be experimentally achieved. So we go from linear to star polymer, bottle brush polymer, dendrimers, and so on, which are schematically drawn here. Now, just quickly, because I see that my time is up, what we observe is that there are qualitative difference already with hard nanoparticles. So first of all, the adhesion strength is linear in the affinity with the gel, which is unlike the hard nanoparticle where the adhesion strength is super linear. But at the same time, the other important thing is that when we use the soft nanoparticle, there is never a weakening of the interface for low affinity. So we don't have a minimum value of the attraction required in order to, let's say, have adhesion. The adhesion can at most drop to 0, but never becomes, say, may never make the system become an anti-adhesive. Actually, the cutest thing, the most interesting thing that we observed, it's however, this one, which is, despite what we hypothesized at the beginning, it looks like the system is actually architecture-insensitive. So what you can see here is the calculated adhesion energy of the interface, the maximum strain and the maximum stress achieved at breakage. And what you basically observe is that independently of the type of architecture, it looks like the only parameter that matters is the total amount of polymer that is present at the interface. And this is pretty interesting. And there are also some hints of that in the literature, in the sense that we checked, and there is nothing about architecture, but as long as we keep the architecture linear, this is consistent with what we observe. Okay, I think we can skip this for the sake of time. Now, regarding this project, in the near future, what is the outlook? Well, basically we are starting to work, well, not starting, but we've been working, and we're starting to look at hard nanoparticles of different shape, again, because packing plays a major role, so there should be a strong effect expected. And in terms of soft nanoparticle, we are starting now to look at hybrid architecture where the nanoparticle, well, basically we don't look just at normal nanoparticle, but we look at nanoparticles that are composed of different polymers. and what can be the effect. And this we can do it actually together with experimental group in the bioengineering department. Okay, that's it for me now, and thanks for your attention. If you want to write any question, I'll be happy to answer at the end.
Thanks, Stefano. Rafi pointed out there was the slide prior to nanoparticles. He wasn't sure about B. If you could pop back to that slide and explain.
Let me do it immediately. Yeah, here. Okay. Yeah, I'm really sorry. I mean, I should have been a lot clearer in describing this, but basically, okay, what is B? B is a parameter that we define as the bridging parameter, and it's given by the formula that you see here in the bottom. So what is C? C is the total coordination number of a nanoparticle, the coordination number being the number of polymer beads that interact with the nanoparticle. And C1 and C2 are actually the beads that come from one half or the other. So what we are looking at when we look at the bridging parameter, it's basically what is the asymmetry in binding at the nanoparticle. So when basically the nanoparticle sits exactly in the middle of the two interfaces, so that it can bind, and it's in the best position to bind the two gel, you would have that C1 is exactly equal to C2, or more or less, I mean, within statistical fluctuation, and that the bridging parameter has its highest value. Whereas when the gel is completely, say, immersed into one of the two, well, sorry, not nanoparticle. When the nanoparticle is completely immersed in one of the two halves, so effectively it has a very high, can have a very high coordination, but there are only a few contacts that are really bridging the two interfaces, then you would have that, I mean, in the limit where the nanoparticle is completely absorbed by one of the two gel, you would have that C1 is equal to C, and then the bridging parameter goes to 1, for at least for high coordination number, but that's the limit we have.
What is the maximum value that C can get?
The maximum value, the thing is, the maximum value that C can get is particle size dependent. So it's not really this C, I mean, only C is the total number of, let's say, polymer beads of the gel that are surrounding the nanoparticle. So the higher the nanoparticle, the larger C will be.
Okay.
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 So, but we don't look, I mean, that's not really the important number. What we're really looking at is how many, the idea was to look at how many of the bonds between the nanoparticle and the gel form are really bridges between the two gels, or they are just bonds that contribute to the, let's say, to the total solvation of the nanoparticle, but they don't contribute to the adhesion of the two gels, of the two halves of the gel.
Right, but I would have thought that this is of relevance, because if the sizes of the nanoparticles are similar to those of the gel, the particles in the gel, then you have the minimal number of possible coordination number, while if you increase or decrease, it changes. And one naively would have thought that this affects the adhesion. And you're saying it doesn't.
Well, no, I'm not saying it doesn't affect adhesion. It's just that we were using this number, I mean, we were using this parameter B to compare, not to compare particle of different size, but we were using to compare what happens when you have particle of the same size, but a different concentration at the interface.
Right, okay.
But obviously, I mean, there are size effects as well.
Yes.
Actually, if you go and check on the paper, which is this Nanoletters number 18, 2018 from us, it explains a little bit more what I was trying to show here in more details.
Okay, fair enough.
Okay. Okay.